This problem can be found at this website along with many other great optimization problems. So for this problem, we are first given just a piece of rectangular sheet metal that was originally 60 centimeters wide, so this whole length was 60 centimeters. And then we just lifted up the sides, so 20 centimeters in length, we lifted up angle theta alongside here too, and what it did, it created a trough along the whole length of the metal. And what we're curious about is what angle measure theta could we lift both the sides in order to maximize the amount of water that the trough can hold. So here we'll just look at a quick visual. So looking at just a quick drawing of a trough, if we're really wanting to maximize the amount of water, we're looking to maximize the volume, but since the trough is just this shape all the way throughout the length, what we really want to do is maximize the cross-sectional area here. So if we can maximize the cross-sectional area, then throughout the length of the whole figure, we'll be maximizing the volume or the amount of water that it can hold. Let's draw a quick picture of the cross-sectional area. So in this drawing of the cross-sectional area, we see our original theta measure here by geometry is equivalent to the theta measure here formed by just taking the straight line across the trough. Okay. We know this is 20. By symmetry of the rectangular lengths, we know this is 20 centimeters as well. And based on the angle measure that we choose, that would change the height and the base. So imagine as you raise the side up higher, that would affect the base and the height of this triangle. Now, we know that if we want to maximize the amount of water in the trough, that means maximize the volume in the trough, which in turn means that we need to maximize the cross-sectional area. We can quickly write a formula for this cross-sectional area. We see that we've got two equivalent triangles here. So we know the area of a triangle is 1/2 base times height. So we're going to say 2 times 1/2 base times height plus the area of the interior rectangle, which is just the length 20 times the width. In our case, we're labeling that h height. And we would get this formula. And here we know if we're going to try to maximize this, eventually we'll want to take a derivative. But what we see currently is that we've got two different variables, base and height. And also, we are curious not about the base and the height. We really want to know what is the angle measure that will maximize the amount of water in the trough. So now we want to take a pause and think, how could we relate the base, the height, back to the angle measure? Specifically, if we zero in on what we're looking at this right triangle, and its symmetric one over here, we could think about how we could rephrase the base in terms of theta and the height. In each case, we know the measure of the hypotenuse. So we could think cosine of theta. That's going to be the adjacent side length divided by the hypotenuse. In our case, the adjacent side length to theta is b. Additionally, we could think of sine of theta, which we know is the opposite side length over the hypotenuse. The hypotenuse is 20, and the opposite side length to theta is h. Now we can solve both of these equations to get b and h separately by themselves. We would get that the base is 20 times cosine of theta, h is 20 times sine of theta, and if we substitute these equations now in for our base and a height, we'll get our area all determined based on this theta measure in a single variable. So let's substitute in these for the values of b and h. Now we'll simply distribute and simplify. And we get that area is 400 times cosine theta times sine theta plus 400 times sine theta. Since we want to maximize the cross-sectional area and thereby maximize the volume, we would want to take the derivative and identify any critical points. So we would take the derivative of this equation and we would get, taking the derivative term by term, we would use product rule to take the derivative of cosine times sine. All times 400 plus 400 times the derivative of sine is cosine. So we get this as our equation for area. Now, as we seek to find critical points, we'll want to see for what theta values could the derivative of area ever equal 0 or not exist. And particularly, this is going to be a bit difficult to solve as we're looking at it written, particularly with this sine theta. So it might be helpful for us to recall the trig identity that sine squared of theta is equal to 1 minus cosine squared theta. By substituting this in for sine theta, we can see if things might simplify a bit more. Perhaps we could factor this. Substituting that sine squared theta is 1 minus cosine squared theta, we'll then distribute the minus and regroup. Now, as we're looking at the simplified expression, we see 2 cosine squared theta plus cosine of theta minus 1, all times 400 is the derivative area. And if we rewrite this in its equivalent form, we might see a bit more of what's going on here. For instance, consider if we just let x be equal to cosine of theta, then we would get that this interior expression is 2 times x squared plus x minus 1, and definitely if we had just seen this as a problem, we would recognize it as something that we can factor. So it's no different that it's cosine squared, or 2 times cosine squared plus cosine minus 1. This could still be factored. And if you need to, feel free to make this substitution and then just, once you've factored it, replace every x with a cosine of theta. So we're going to consider, where does this derivative equal 0 or not exist? So here we would have 0 equals this. Of course, we could divide both sides by 400 and we would just get 0 equals this expression. And as I said, if we're looking at how to factor this, think about if it helps replacing every cosine with the x, then this expression could be rewritten as this, which we could quickly see factors to 2x minus 1 times x plus 1. It would hold here, except now we would just write it as 2 cosine theta minus 1 times cosine of theta plus 1. Now by the zero product property, we know that this times this only equals 0 if this equals 0 or if this equals 0. Let's consider those cases. For the first one, we would add 1 to both sides. 2 cosine of theta equals 1. Divide both sides by 2. And we would get cosine of theta equals 1/2. And we would just think, what values? Remember, if we're starting with a piece of metal that's flat, and then we're lifting it up, okay, we would consider lifting it everywhere up to about 90 degrees. That would make a rectangular trough. So we would be looking at angle values between 0 and 90. We wouldn't want to surpass that if we're making a trough. So we think, what values of cosine, theta values from 0 to 90, that cosine of theta is 1/2. And that would give us theta is pi over 3. Similarly here, we could subtract 1 from both sides. And we'd need to consider, when is cosine of theta equal to -1? So on the unit circle, that would occur here at pi. So that would be at pi, or at theta equals pi, but this doesn't make sense in our context, because that would mean we would start off with the flat piece of metal hinged here, we would lift it past 90 degrees and lift it all the way flat again. So just in context, this doesn't make sense to be one of our critical points for this particular problem. So we would only be looking at the critical point theta is pi over 3. Now this problem has some specific endpoints. Since we're looking at theta values, we know at the beginning when the piece of metal was flat, theta was 0. And we could consider all theta values up until when we got the rectangular trough at 90 degrees. So our endpoints are theta equals 0, theta equals 90 degrees. And our only critical point is theta is pi over 3. And for continuous functions on a closed interval, remember you can identify the absolute max and min by evaluating each of these points into the original function and just seeing which would give the highest or lowest output value. So we could quickly make a table to determine where our maximum value would come from. And in this case, I'll write 90 as pi over 2, stick to radian measures. So recalling back the area formula that we found earlier, we'll just substitute these in, complete the table. We see when calculating that when theta is pi over 3, we would get the maximum area of 519.615. And in this case, a maximum cross-sectional area would give us a maximum volume. So for our problem, theta should be pi over 3 to give us a maximum amount of water in the trough.